But we're going to start with the warm-up question for today before we get into those notes. The warm-up question says, Ben needs to move the crate 6 meters to the right. What changes would cause him to do more work? And on my next slide, I have some different changes that we can take a look at one by one. Okay, so I want you to think and ask yourself this question: will this change result in more work? All other things remaining equal, will pulling this more horizontally result in him doing more work? Yes. Okay, if everything else remains equal, then yes. If he pulls it more horizontally with that same amount of force, that will be more work. We looked at that example the other day. But right now, he's pulling at an angle of 30 degrees. If he makes that angle smaller, or even if it's completely horizontal, the closer he gets to that, the larger the component of his force that is horizontal. Of course, if it's completely horizontal, the whole thing is being used to do work. But yes, pulling it more horizontally would result in more work. What if he carries it instead? No, in fact, that would be no work at all. We've talked about that example a couple of times. Okay, we need some component of his force to be parallel to displacement, and carrying it would be perpendicular. Okay, what if he pulls it faster? All other things remaining equal, will pulling it faster result in more work? Look at your work equation. Does this equation take into account how fast you pull it? No, that's because it's not a factor that affects it. Not in the formula, does not affect the work. So the rate at which he pulls that crate will not affect the amount of work that he does. What if he pulls it a farther distance? Yes. Again, there are only 3 variables in this equation for work. Force, so using more or less force will affect your work. Displacement, having a greater or smaller displacement will affect your work. And cosine of the angle theta, the angle will affect the amount of work. Okay, but that's it. Anything else, don't get thrown off by it, don't get tripped up by it. It's not going to affect your work because it's not in that formula. Okay, please make sure you have put your answers to this warm-up question in My Open Math. As I said, we have some notes today, and we're going to be talking about energy, specifically kinetic energy, which I've been mentioning a little bit yesterday, and I said, hey, we're going to be talking about this over the next few days. That's going to start with today's notes. But before we talk about kinetic energy, let's go ahead and get a definition for just energy in general, because kinetic energy is, of course, a form of energy. And guys, I'm going to strongly encourage you to take notes today, because a lot of today's notes are actually just example math problems that are going to be pretty similar to what show up in your problem set or the types of questions that you could see on your quiz or on your test. All right, so energy is defined as the ability to do work or cause movement. And it's kind of a vague definition, because ability to do work, we've already talked about work. The definition for work was a measure of energy transfer, okay, that is caused by a force applied to move an object some displacement. Okay, and so both of the definitions kind of refer to each other, so it's a little bit weird in that way, and it's hard to define some of these more abstract terms. Okay, but it is the ability to do work or to cause movement. That part's a little bit easier to visualize. And energy is always carried by something, usually in the form of movement, which is what we're going to focus on today, but it can be stored in many different forms. And we will get into other forms of energy later on. We're not going to talk about them today. Today we're going to focus specifically on kinetic energy. Kinetic energy is energy associated with an object's motion. The energy an object possesses due to its motion will be the kinetic energy of that object. Therefore, if the object is not moving, if you have an object at rest, that object will have no kinetic energy. It has to be in motion in order for it to have this energy of motion. We have an equation for kinetic energy, which I have abbreviated KE, kinetic energy. And the equation for kinetic energy is equal to, KE equals 1/2 mv squared, where m is your mass and v is your velocity. When you use this equation, you are only squaring the velocity. Please don't square the whole thing. Okay, one other thing you're going to want to make a note of is that when you use this formula and substitute numbers into it, your masses must be in kilograms. So if you read a question and it talks about a 400-gram baseball, please don't plug that number in. It needs to be converted to kilograms first. Some of you forgot to do that In the last, on the RA that you had with your bumper stuff, I had a few people that did their calculations with their cart in grams. Okay, we don't use grams in any of our calculations. You need to convert to kilograms for every calculation we've done this year. In case you still don't remember it, you might want to write down the conversion factor. There are 1,000 grams in a kilogram. Okay, so it should be a pretty easy conversion to get from one to the other. So again, make sure you're in kilograms. Velocities, likewise, must be in units of meters per second. So if you have a velocity given to you in miles per hour, kilometers per hour, whatever, any other unit, it will need it to be converted into meters per second. And that is so that we end up with the correct units at the end. When we do our calculation for kinetic energy, we want our unit in joules. Bless you. A joule is a Newton meter, and a Newton meter, again, that's the same unit, by the way, we used for work, okay, Newton meter or joule, and that is equal to a kilogram meters squared per second squared. That's why we need to use those units, because that's what we end up with. And if you have kilogram meters squared per second squared, that is a joule. It's obviously much shorter to write just a capital J, and it is a capital J whenever you're typing it in MyOpenMath. Just so you're aware, there are other units that can be used for energy. We don't use them in this course, but calories are also an energy unit. We talked about that because it's the same two units we talked about for work. Since work is energy transfer, work and energy have the same units. Joules, calories. Now for this course, everything we're doing is in joules. If I ever give you an energy or work in calories, I will also provide you with the conversion factor. You don't have to memorize it. It will be given to you, but if you do ever see calories, please convert it. All right, so looking at the equation, we can see there are two factors that affect kinetic energy because Ke equals 1/2 mass times velocity squared. Both mass and velocity will affect or determine the amount of kinetic energy that an object possesses. So let's take a look at each of those relationships. Mass and kinetic energy. If I double the mass of an object, okay, or maybe I'm comparing two objects that are otherwise moving exactly in the same way, but one of them has twice as much mass. It's easier to do than doubling the mass of something. Okay, then my kinetic energy will be 2 times as much. Again, this is a type of question you might see. Okay, this is a proportional reasoning question. But if you double this value for m, you will get 2 times the answer over here for Ke because they are directly proportional to one another. You need to be able to answer questions like that. If I triple it, if I half it, whatever, and tell me what happens. But because it's directly proportional, and you should be able to see that looking at the equation, any change that you make to the mass of the object or any comparison where you're comparing two different masses, you're going to have that same change, or it's going to change by the same factor for your Ke. So 4 times the mass, 4 times the Ke. 1/2 the mass, 1/2 the Ke. Okay, on the other hand, when we look at the relationship between velocity and kinetic energy, it's a little bit different because in the equation, it's Ke equals 1/2 mv squared. Because the velocity is squared, we're no longer looking at a directly proportional relationship. If I double the velocity, it does not double the kinetic energy. It does make it bigger, but not by a factor of 2 because it's being squared. So if I double the velocity, my Ke will change by a factor of 2 squared, which is a factor of 4. If I triple the velocity, it will change by a factor of 3 squared, which would be a factor of 9. Okay, this is a squared relationship. It is exponential. Okay, I've also shown you what these two types of relationships look like graphically. A directly proportional relationship between kinetic energy and mass will give you a linear graph. A squared relationship, an exponential relationship between kinetic energy and velocity will, of course, give you a curve, like you see down here. Okay, so you do need to be able to recognize those relationships. You need to be able to answer questions. If I, have half as much, what happens? And maybe even recognize what the graph looks like. All right, let's do an example calculation for kinetic energy. It says, calculate the kinetic energy of a 5.2 kilogram object moving at 2.4 meters per second. Again, it is a good practice to label everything when you read the question. Okay, this particular question wants me to find Ke, and it gives me a mass, and it gives me a velocity. Okay, so from that, KE, mass and velocity, if I look at the equations I have, it's the one we just learned. Kinetic energy equals 1/2 mass times velocity squared, and we can substitute into that formula, which looks like this. KE equals 1/2 times 5.2 times 2.4 squared. Half of 5.2 is 2.6. 2.4 squared is 5.76. And then we can multiply those two numbers, or you can do it all at once if you want, and you'll get the same thing, 14.98 joules. Okay, so if you have a kinetic energy calculation, it's still pretty straightforward. There's only 3 variables in the equation. I can give you any 2 of them and ask for the third. Okay, so I could give you mass and velocity and ask for KE, but I could just as easily give you KE and velocity and ask for mass, or KE and mass and ask for velocity, which is what we're doing in this one. An object has a kinetic energy of 52 joules and a mass of 13 kilograms. How fast is the object moving? So again, when you read it, label it. I have a kinetic energy, I have a mass, I'm looking for velocity. I'm still using my kinetic energy equation. KE equals 1/2 mv squared. Substituting in looks like this. 52 equals 1/2 13 times v squared. Half of 13 is 6.5. If I divide both sides by 6.5, I can get that v squared by itself. 52 divided by 6.5 is 8, which is not my answer because it's v squared. You have to now take the square root of 8, which will give you approximately 2.8 meters per second. Okay, does anybody have a question about the kinetic energy calculations? Hopefully pretty straightforward. It's only got 3 variables. A little bit trickier equation since you do have something squared in here, so just be careful when you're typing it in the calculator. Don't forget to square that velocity. Okay, so we know how to find kinetic energy, but how about situations where we have changing kinetic energy? How can we change the kinetic energy of the object? Well, again, we've already looked at the factors that affect it, mass and velocity. It's pretty tricky to change the mass of an object. We don't really do that, but it's really easy to change its velocity. Okay, so we're going to focus on changing the velocity of the object and thus changing its kinetic energy. Guys, how can I change the velocity of an object? Cause it to accelerate with a force. I just heard both terms. Okay, I can have an impulse, a force applied for a certain amount of time that will cause an acceleration. Okay, again, if you push it, if you pull it, if there's friction, if there's any external force acting on that object, we're going to have a change in the velocity of that object, which means we're going to have acceleration, and thus our velocity changes and our kinetic energy changes as a result. Okay, so let's take a look at some examples of that. Okay, so here is our first example. And guys, when we start looking at this, every single equation we've used all year, I wrote them all back on the board today because they are all fair game. I can ask you to use any of them. Okay, they're all up there. You can write it down. Okay, so this one says, a ball with a mass of 2.1 kilograms rolls across the floor of this room. If it has an initial velocity of 6.4 meters per second and experiences an impulse of -5 Newton seconds, what is its final velocity? Find its change in kinetic energy. So guys, if I look at this question, I have a mass, I have an initial velocity, and I have an impulse. That looks like something I saw last unit. In fact, it looks like this. I know that impulse is equal to change in momentum, which is equal to mass times change in velocity. Therefore, impulse equals mass times change in velocity. That's the information I have, and so that's the equation I'm going to use. So I'm going to set my impulse, -5, equal to my mass, 2.1, times my change in velocity. Again, change in velocity is VF minus VI. So I have VF minus 6.4 in this particular case. Okay, and now we can solve for that final velocity. And if we know how fast it's going at the end, we can figure out what its kinetic energy is. Okay, so that'll take us to the second step. Okay, but first, let's go ahead and get VF by itself. You could distribute that 2.1, or I could just divide both sides by 2.1. -5 divided by 2.1 would equal VF minus 6.4, and of course -5 divided by 2.1 is -2.38. Now I just need to add 6.4 to both sides. 6.4 plus -2.38, or 6.4 minus 2.38 gives me a final velocity of 4.02 meters per second. Okay, so I have answered the first part of this question. I now know the final velocity of this object. It makes sense. It should be slower because the force that was applied, or rather the impulse, was negative. It was working against the direction of this object's motion and displacement, so I slowed down from 6.4 to 4.02. I know I have a change in KE, now I just have to figure out what it is. If you are asked to solve for a change in kinetic energy, you can do that by finding your final kinetic energy and your initial kinetic energy and subtracting them. Change in anything is final minus initial. Change in velocity was final velocity minus initial velocity. Change in position was final position minus initial position, which was displacement. And change in kinetic energy will be final kinetic energy minus initial kinetic energy. So we need to find each of those. Initial kinetic energy, we're still going to use our kinetic energy equation, KE, in this case KE initial, so KEI, equals 1/2, the mass is 2.1, the initial velocity is 6.4 squared. If I multiply that all out, I get an initial kinetic energy of 43.01 joules. Final kinetic energy, we're going to do exactly the same thing, except now I have my final velocity in the equation. That's the one I just solved for. So I have 1/2 times 2.1 times 4.02 squared. When I multiply that out, I get a final kinetic energy of 16.96 joules. Now I can figure out my change, because I went from 43.01 to 16.96, so I lost some energy, which I know because I slowed down. Okay, my force was negative, my impulse was negative, I slowed down. Okay, so how much did I lose? Again, you can look at that and probably reason your way through it to figure it out, or you can go algebraically to this equation, delta KE, change in kinetic energy, equals final minus initial kinetic energy, and plug in those numbers. 16.96 minus 43.01 gives me a change of negative 26.05 joules. Make sure your answer makes sense. If you slowed down, you should have a negative delta KE. If you sped up, it should be positive, okay, because that is telling us what our change in energy is. If we get slower, we lose kinetic energy. If we get faster, we gain kinetic energy. So make sure your sign makes sense. Okay, does anybody have a question about this problem? All right, let's try another one then. All right, so this one, we had to use stuff from last unit. We had an impulse. This one, a little bit different. It says a 151 gram toy car is pushed from rest with a force of 0.67 newtons for 1.4 seconds. What is its change in KE? Okay, so I've labeled some information. I guess I could have also labeled my initial velocity of 0. I didn't put that up there, but I could have. Okay, and I'm looking for change in KE. But before I go any further, there's one thing I need to address. Am I allowed to leave it like that? No. Don't go any further. Check your units. Don't leave grams in there. Okay, 151 grams is 0.151 kilograms. Fix that first. Now we can move forward. Okay, we need to determine our change in kinetic energy, but in order for us to figure that out, we need to know what our initial velocity and our final velocity are, so that we have the velocities that we need to figure out our initial kinetic energy and our final kinetic energy. Okay, so I need to find my final velocity. I know my initial velocity, it's 0. I forgot to label it, but it says from rest. Okay, and once I get both of those, I can find my change in kinetic energy. So I've got to do this in 2 steps, starting with finding my final velocity. Well, guys, if I have mass, force, time, I can find my change in velocity. That's also an equation from last unit. It's just a different one than the one I used a second ago. I can use this equation. Again, all of these are fair game. You have to be able to look up here. That's why you need to label stuff. Okay, force times time equals mass times change in velocity. Plugging in, that looks like this. 0.67 times 1.4 equals 0.151 times my delta V, my change in velocity is VF minus VI. My VI was 0, so VF minus 0. Okay, now if I go ahead and multiply that, 0.67 times 1.4 is 0.938. It's equal to 0.151 times VF. I dropped the minus 0. Okay, from here I'm going to divide both sides by 0.151 and I will get a final velocity of 6.21 meters per second. Okay, so I have this toy car that was at rest and then I pushed it and I made it move, so now I have velocity. I have therefore gained kinetic energy. I just need to figure out how much kinetic energy I gained. Okay, but now that I have a final velocity, I can figure out what my final kinetic energy is, and I know my initial kinetic energy was 0 because it was at rest. Okay, so my initial KE, 0. My final KE, we're going to solve for 1/2 mv squared. Substituting in, that's 1/2 times 0.151 times 6.21 squared. And that is going to give us a final kinetic energy of 2.91 joules. So guys, what's my change in kinetic energy going to be? If I started with 0 and now I have 2.91, what's it going to be? Positive 2.91. Okay, you don't have to do that algebraically. You can. Looks like this, 2.91 minus 0. Okay, which of course is positive 2.91 joules. This toy car has gained 2.91 joules of kinetic energy because we pushed it. Okay, questions about this one? All right. Let's try this one. Okay, I've already had you use 2 different formulas from last unit. Okay, let's see what I give you this time. It's different. Okay, a 14 kilogram wagon initially moving 3.7 meters per second accelerates at a rate of negative 1.2 meters per second squared as it rolls across rough pavement for 1.4 seconds. What is its change in kinetic energy? Okay, again, I can find change in kinetic energy if I know my initial kinetic energy, which means I need an initial velocity, and I know my final kinetic energy, which means I need a final velocity. So although it's asking me to find change in KE, I first need to find my final velocity, and then I can find my change in kinetic energy. Okay, so I've got 2 different things I'm looking for. What equation can I use to find VF from the information I have? I gave you different stuff again. The very first equation on my board, you're absolutely right, Austin. VF equals VI plus A times T. I got to use a kinematic equation this time. I told you these are all fair game. Okay, so now we're going to use a kinematic equation, specifically this one. VF equals VI plus A times T. Substituting in, that looks like this. VF equals 3.7, that's VI, plus negative 1.2, that's A, times 1.4, that's T. Guys, don't forget the negative sign on your acceleration. You will get the wrong answer if you forget the negative sign. Okay, so when we multiply negative 1.2 times 1.4 and we add it to 3.7, we get a final velocity of 2.02 meters per second. Okay, so we have our final velocity. Okay, which means we can find our change in KE because we can find our kinetic energies. Okay, we're going to have an initial kinetic energy because it was initially moving 3.7. Now it's only moving 2.02, so it did lose some of it. I already know my change will be negative. Okay, but I have to solve for my initial KE and my final KE. Initial KE, 1/2 times 14 times 3.7 squared. Gives me an initial kinetic energy of 95.83 joules. My final kinetic energy, same idea, different velocity, 1/2 times 14 times 2.02 squared, gives me a final kinetic energy of 28.56 joules. From here, I just have to subtract. I know that I lost quite a bit of energy because I went from 95.83 to 28.56. I just need to know how much I lost. Okay, so I'm going to be plugging into this equation. Delta KE equals final minus initial kinetic energy. That's 28.56 minus 95.83, which of course is a change of negative 67.27 joules. Does anybody have a question about this one? As you can see, it's going to be really important for you to label things because now we have so many variables that we can pick from and we have so many equations to look at. Label them. It may also benefit you to draw a picture, especially if it starts talking about forces. A free body diagram might be helpful to you, okay, depending on the question. So you should have paper out as you work through your assignment today. 601.2 kinetic energy problem set. It has 10 questions, and it's due by 11:59 p.m. tonight. You guys have the remainder of the class period which we're on advisory schedule, so you've got 20 minutes. So you've got a fair amount of time to work, and of course there's advisory after that. But anything that you don't finish in class will be homework. Okay, so again, go ahead and get started. If you have questions, please let me know.